Welcome to The Explainer. Today we're diving straight into one of the most breathtaking connections in modern theoretical physics and mathematics. We're going to bridge the abstract algebra of the Grothendieck Katz p-curvature conjecture directly to the physical reality of Lagos field theory and emergent spacetime. This is literally where pure number theory becomes the very fabric of our universe.
Okay, so here's our roadmap for today. We'll be moving through 6 key sections, zooming all the way out from microscopic, local algebraic primes, right up to macroscopic gravity and emergent spacetime.
Let's jump into Section 1, the local-to-global bridge. We begin right at the microscopic level to introduce our foundational mathematical problem.
Now, what's really fascinating here is how the Adelic Langlands Program completely transforms our starting point. You see, where the Grothendieck-Katz conjecture requires vanishing p-curvature for almost all primes, this machinery takes that localized problem and lifts it globally. It transforms it into the trivialization of the local Hecke operator, represented here by T of p transforming to 1. We are essentially lifting the connection from a local curve entirely globally onto the ideal ring.
Notice the exact translations taking place in this breakdown. The classical vanishing of p-curvature literally becomes the trivialization of the local Hecke operator across the Adels. And that requirement, the one that says this holds for almost all primes, that simply means the automorphic representation is unramified almost everywhere. The classical finiteness of global monodromy is actually achieved through the trivialization of global Galois perimeters. It's a perfect mathematical translation.
Moving on to Section 2, rigidity and L functions. Let's see how this all builds into these massive global mathematical frameworks.
Right here is where the magic really happens. Through the Sadaka isomorphism, we map the local Hecke algebra to symmetric polynomials over the complex Langlands dual group, denoted as SP mapping to those complex polynomials. By doing this, the local p-curvature is revealed to be the semi-classical limit of the local Hecke operator at a non-Archimedean place p. The local p-curvature operator and the local Hecke operator are fundamentally, undeniably tied together.
So the crucial point here is that when those local p-curvatures actually vanish, the global L function collapses into this incredibly precise zeta-like structure. It becomes an infinite product over exceptional primes and standard Riemann zeta functions. And when we impose the universal Langlands functional equation onto this collapsed structure, it mathematically forces the parameters to be roots of unity. This pure algebraic rigidity mathematically dictates that the global geometric monodromy has to be finite, which proves the solutions are algebraic.
So we've successfully established that differential equations must look trivial to almost all p-adic stabilizers unless their overarching geometry is finite. But take a second to really let that heavy math sink in. How do these purely algebraic constraints, sitting quietly in abstract number theory, actually generate the dynamic waves and physical operators of field theory?
That brings us to Section 3, the Logos field D'Alembertian. We are now crossing the bridge into macroscopic fields.
Take a look at the D'Alembertian operator here. The smooth, macroscopic wave operator of Lagos field theory is mathematically realized at a finite prime p as a nested infinitesimal commutator of the local Hecke operator, with the local derivation on the Beilinson-Drinfeld-Grassmannian. We are quite literally watching a second-order Laplace-Beltrami operator be born directly from local arithmetic derivations.
And this brilliantly illustrates why the whole thing works. When we expand this nested commutator over a characteristic p base, the binomial expansion kicks in. Because we're working modulo p, all those intermediate cross terms, where the binomial coefficient is not divisible by p, they vanish identically. They just drop out. The entire field theoretic chain collapses perfectly onto our algebraic p-curvature tensor. The macroscopic wave equation is the exact physical manifestation of this arithmetic commutator.
Section 4, the exceptional set. To fully understand this field, we have to look at what happens when our perfect arithmetic D'Alembertian encounters a non-trivial error.
This visual dichotomy is absolutely vital. For regular primes, where p-curvature vanishes, we get pure vacuum stability. The quantum error correcting code runs flawlessly, zero physical entropy is generated. But for the exceptional set, what we call the bad primes, that commutator is non-zero. And that injects localized topological vortices, or arithmetic friction, right into the field.
Now, to keep these wild ramifications from breaking the computational integrity of the entire system, the local root number, represented by W, steps in as an exact arithmetic phase calibrator. Because the inertia invariant subspace drops in dimension, which causes the Swan conductor to spike, the local L function actually loses its tracking ability. So the complex root number absorbs that topological curvature defect, shifting the scattering matrix just enough to maintain global coherence.
Section 5. Sourcing the stress-energy tensor. Now we get to translate these stabilized arithmetic defects directly into the physical mass and energy of our universe.
Look closely at this coupling identity. That non-zero commutator mathematically prevents parallel transport. It creates a structural snag in the math. Notice how the Dirac delta function confines this structural friction perfectly to the Adelic coordinate of the defect. This friction generates local energy density, which perfectly defines our macroscopic stress-energy tensor.
By evaluating the microlocal derivative of the epsilon factor with respect to the scaling parameter s, we arrive at something truly incredible. The physical stress, the actual mass energy injected into the Lagos field, is exactly proportional to the arithmetic ramification depth of the non-vanishing p-curvature. The log p weight, multiplied by the dimension drop and the Swan conductor, dictates the exact amount of localized physical stress. It's a perfect one-to-one mapping.
This matrix powerfully breaks down how the mathematical properties of the defect become literal, observable physics. The time-time component, energy density, is dictated by conductor depth. Mass is literally just the localized structural debt of a non-vanishing p-curvature. The spacetime momentum flux tracks the Frobenius eigenvalues, acting like solitary waves or solitons. And the space-based shear stress maps directly to the nilpotency index of the p-curvature tensor.
Okay. So we now have a mathematical mechanism giving us mass, energy, momentum, and shear stress, all born from a modulic code-correcting arithmetic errors. But how do these localized, highly specific arithmetic defects actually generate the grand, sweeping gravitational curves of spacetime as we observe it? Let's find out. Section 6. Emergent spacetime in geodesics. Let's step out into the macroscopic universe and look at the final grand readout of this incredible framework.
We finally arrive at the Einstein-Logos equations. In this theory, smooth spacetime isn't just an axiomatic background that exists for no reason. It's an emergent readout. The Grothendieck-Riemann-Roch push-forward takes the arithmetic Gillet-Soulé metric and projects it down, coupling the informational stress-energy tensor directly to the standard Einstein tensor, g mu nu. The physical metric of our universe is directly warped by the algebraic defects of our exceptional primes.
If we unroll the Riemann tensor, this illustrates the ultimate mapping across two distinct channels. The Ricci tensor, the mass-energy curvature, is exactly identical to the arithmetic ramification density. Spacetime contracts because wild ramification creates a volume deficit in the push-forward. Meanwhile, the wild tensor, the tidal conformal curvature, is sourced trace-free by the nilpotent shear of the p-curvature deforming the underlying prime fibers.
Because the Riemann curvature is explicitly sourced by these local arithmetic indicators, the metric's Christoffel symbols are fully determined by the exceptional set. When a particle travels along a geodesic, it isn't feeling a classical Newtonian force pulling it. No, it is merely navigating the semi-classical shadow left behind by the local Langlands epsilon factors as they diligently stitch together the arithmetic fractures caused by non-vanishing p-curvatures.
I want to leave you with this final, profound thought from our source material. Space-time geometry is the error-corrected tapestry of number theory. What we experience every day as a stable, massive particle is actually a localized topological defect held in equilibrium by p-adic stabilizers. But if our macroscopic universe, our gravity, our entire reality is just the semi-classical shadow of Adelic error correction, what deeper underlying computations are yet to be discovered? Keep wondering and keep learning. Thanks for joining me.